Okay, so some of the excess carbon dioxide is taken up by plants or is dissolved in the ocean, but an estimated 45% remains in the atmosphere. The bottom and the right images that you have right here show the CO2 concentrations that were found in an ice core from Antarctica, from again 800,000 years ago, or up until 800,000 years ago. And as you can see in the bottom image, you also have the delta 016 to 018 temperature proxy showing a pretty good correlation with the CO2 concentrations, which again are a proxy for temperature data itself. So we see from these graphs that the CO2 concentrations in those 800,000 years have remained between 180 and 300 parts per million. But as we can see in this right top image, over the past century or so, we've gone more than 30% of the highest concentration seen, or 30% over the highest concentration seen in those 800,000 years. So again, now we're pretty much at 400 parts per million, something that hasn't been seen at least in 800,000 years. So along with this carbon dioxide concentration increase, we have also measured the temperatures to be higher on average in the world. And again, measured is a pretty key word. And more, we have seen that these temperatures have been higher in areas that are closer to the poles than areas that are closer to the tropics, for example. So the left image that you have right here kind of shows you a difference in the temperatures for different locations in the Earth from, or as a contrast between 1980 from 1951. And you see the changes there. So you see that the greatest temperature increase is mostly seen here in the Arctic Circle for the most part. And it's relatively different throughout the rest of the subtropics and tropical areas. There's not much data here in the southern hemisphere, but there's believed to also have seen temperature increases as of more recent times. So again, granted, there are a lot of assumptions to be made in the case of data collection. Assumptions like where temperature measurements are actually being done, what the equipment is and what it is and where it's made. Also, the equipment that was being used since the measurements began has changed radically to the one that we have today, and their accuracy also has changed. The frequency at which these measurements are taking also has a huge effect. There's also a big bias for the different environments that come along with the data acquiring, the human error, the political reasons behind things. So even though there are, again, a lot of assumptions to be made in the case of data collection, thus far, what the measurements have indicated is that we do see this temperature increase throughout the globe. And it is, for what we think, very much linked to the rising levels in carbon dioxide. So in short, it appears as though the temperatures have risen, and we attribute this rising of the temperatures to the larger CO2 concentrations. So according to the Intergovernmental Panel of Climate Change, or the IPCC, as I will refer to it later, this warming of our planet is unequivocal, and it is now evident from observations of different things. So observations on the increases in the global average air and ocean temperatures, in the widespread melting that we're seeing for the snow and the ice around the globe, and in the rising global sea level, for example. According to the IPCC, it's also extremely likely that this rise in temperatures is an effect from the human-generated greenhouse gas concentrations. This indicates a probability of 95 to 100% that this is the case. So the average increase in temperature is of 1 degree Celsius since the late 19th century, with most of that warming occurring during the last 35 years, as you're seeing here in the graph. A pretty big spike right here. So the image here on the top right again shows the change in degrees Celsius that were observed around the globe in those 29 years between 1951 and 1980. And you see that it changes geographically. The rise in temperatures globally it doesn't mean that each year there will be a greater temperature than the last year. So it doesn't mean that next year will be hotter than this year necessarily, because there are still some fluctuations. But it is expected that each decade is going to be warmer than the last decade in average. So predictions of this future climate are pretty hard to make because they are typically done by models. And as I said earlier, all models are wrong, but some are better than others. And all of them must make some assumptions about the system under which they're working. So using a few different values for the input of human-generated greenhouse gases into the atmosphere, the IPCC came up with this graph in the lower right that you have of the slide. And each of these lines that are on the right represent a different scenario of carbon dioxide concentration values in the next century or in this century. So the bottom line represents the values of human-generated carbon dioxide if they were similar in input to the values that were emitted in the year 2000. Overall, it is very unlikely that the temperature rise is going to be any less than 1.5 degrees Celsius over this century, meaning that there is only a probability of 1 to 10% that this is the case. It's going to be more likely that due to the CO2 concentration increasing by human-generated activities, that the rise in temperature will be greater than 1.5 degrees Celsius. Some of the worst case scenarios projected to be as high as 4.5 degrees Celsius. So carbon dioxide is not the only gas that is contributing to temperature increase. In more recent years, atmospheric scientists have found that human industrial and agricultural activities are actually causing buildup of many other trace gases that also play significant roles. So they receive their name of trace gases because their atmospheric concentrations are actually a lot smaller than the carbon dioxide. So remember, carbon dioxide is present in the atmosphere at about 0.04%. These trace gases are much, much smaller in concentration. So the most important trace gases are methane, nitrous oxide, and the chlorofluorocarbons, or CFCs. So these gases, just like carbon dioxide, absorb the long-wave radiation from Earth to space, and hence will aid in the warming of the lower atmosphere. So now we're going to go ahead and cover each gas independently. So let's go ahead and start with methane. So methane is about 20 times as effective at absorbing the long-wave radiation than carbon dioxide. And so, although its concentrations are much lower than the carbon dioxides, its impact is quite great. So methane is produced by anaerobic bacteria in wet places for the most part. Anaerobic itself means an environment that has low oxygen or no oxygen at all. So for the most part, methane is produced in areas where the oxygen is scarce. Environments like these are places like swamps, bogs, wetlands, or paddy fields which are artificially flooded to grow rice. But methane is also produced inside the guts of termites or of grazing animals like cattle and sheep. So methane is also released when drilling for coal and oil, because it is associated with the environment of formation of these resources. So remember that coal and oil also form in this organic rich kind of areas. So methane forms in these areas as well, and it gets buried within the strata. So it formed a long time ago with them, and by the drilling of the fossil fuels, we are also releasing some of that paleomethane, if you would. Okay, now let's go ahead and cover nitrous oxide. So nitrous oxide is sometimes referred to as the laughing gas. It comes into the atmosphere by the agricultural industry for the most part. So nitrogen is a huge component of many of the fertilizers that we use, and sometimes part of the nitrogen of the fertilizers enter the atmosphere and reacts with the oxygen to form nitrous oxide. So some of it also comes from high temperature combustion of fossil fuels. The rate at which it has entered into the atmosphere is a little slower than the rate at which methane has entered the atmosphere, but the nitrous oxide is actually 300 times as effective as carbon dioxide at absorbing the long-wave radiation. So much better at absorption than CO2 or than methane. And a worrisome fact is that although the rate at which it has entered the atmosphere over the last few centuries is lower than the rate at which methane has entered the atmosphere, we have seen a greater rate during the last few 30 years, I think, or so. So nitrous oxide is entering the atmosphere at a greater rate than methane as of recent years. Okay, so lastly we have CFCs, or chlorofluorocarbons. Chlorofluorocarbons are not naturally present in the atmosphere, and these are manufactured chemicals that have many uses. These have gained notoriety because they are responsible for ozone depletion in the stratosphere. Despite knowing this fact that they contribute to the ozone depletion, we don't really know much about their role on global warming. But thankfully, CFC emissions have practically stopped in developed countries. But unfortunately, they do remain in the atmosphere for decades, so they could still cause some harm to our atmosphere, even though their emission has basically stopped. So, after accounting for these trace gases effects, along with the CO2 effects, we expect the temperatures to rise even faster than just by accounting with the CO2, unfortunately. So some of the sophisticated computer models show that the warming of that lower atmosphere will not be the same everywhere. Rather, the temperature response in polar regions could be 2 to 3 times greater than the global average overall. And this has to do with a few things, one of them being the large stability of the troposphere in polar regions, where the vertical mixing of air is suppressed. So there's not very much mixing occurring, and so much of those trace gases along with CO2 kind of remain pretty stable at the polar regions and don't intermix more. So unfortunately, humans contribute more than just greenhouse gases to the atmosphere. Although this is the main impact that we have on global warming, we do have other effects. So remember that aerosols are tiny liquid and solid particles that are suspended in the air. And we do have some aerosols that we emit to the atmosphere as well. So most of the human generated aerosols come from two sources, the main one being sulfur dioxide emitted during the combustion of fossil fuels, and the second one being from smoke from vegetation that is burned to clear the agricultural land or land used for mining, etc. So human-generated aerosols act in the same way as naturally emitted ones. So they are going to block solar radiation, that solar shortwave radiation.